Hello and welcome. Imagine you are sitting in the driver's seat of a car, but you are not driving. Your hands are not on the steering wheel, and your feet are not on the pedals. The car is navigating complex city streets, merging onto highways, and stopping for pedestrians, all on its own. This is not magic, it is the result of decades of scientific and engineering progress. This is the world of self-driving cars. But how do they truly work? How does a machine, made of metal and silicon, perceive and understand the chaotic and unpredictable world of human driving? To understand this, let us first think about how you drive. You use your eyes to see the road, other cars, traffic lights, and signs. You use your ears to hear sirens or the honk of a horn. Your brain processes all this information instantly, making decisions like when to brake, when to accelerate, and when to turn. A self-driving car does the exact same thing, but it uses a suite of sophisticated sensors and a powerful computer instead of eyes, ears, and a brain. The most crucial step for any self-driving car is perception, understanding its environment. It cannot guess, it must know with a high degree of certainty what is around it. To do this, these vehicles are equipped with three primary types of eyes. The first is the camera. Just like the camera on your phone, these visual sensors capture images and video of the car's surroundings. They help the car identify things like the color of a traffic light, the text on a stop sign, or the outline of a pedestrian crossing the street. However, cameras have a weakness. They struggle with depth perception and can be blinded by harsh sunlight, heavy rain, or fog. This is where the second type of eye comes in, radar. You might be familiar with radar from weather reports or air traffic control. Radar sensors on a car constantly send out invisible radio waves. These waves bounce off objects and return to the sensor. By measuring how long it takes for the wave to return, the car can calculate the distance and speed of objects around it. Radar is excellent for tracking the movement of other vehicles, especially in bad weather where cameras might fail. But the true superstar, the technology that gives the car a superhuman sense of its world, is the third eye, LiDAR. In our next part, we will dive deep into this incredible laser-powered technology and see how it creates a live, three-dimensional map of the entire world around the vehicle. In our last part, we talked about how self-driving cars use cameras to see like us and radar to detect the distance and speed of objects. Now, let us meet the technology that truly sets these vehicles apart, LiDAR, which stands for light detection and ranging. Imagine if you could instantly create a perfectly detailed, three-dimensional map of everything around you, down to the centimeter. That is precisely what LiDAR does. A typical LiDAR unit is that spinning cylinder you often see on top of self-driving test cars. It works by firing millions of tiny, invisible laser pulses every single second in every direction. Each laser beam hits an object, a tree, a curb, another car, a person, and reflects back to the LiDAR sensor. The system measures the exact time it takes for each light pulse to return. Since we know the speed of light is constant, the car can calculate the precise distance to every single point that the laser touched. By combining all these millions of distance measurements, the car's computer builds a real-time, 360-degree, three-dimensional map of its environment. This map is called a point cloud, and it looks like a detailed digital replica of the world, showing the exact shape and position of every object. This laser-powered perception is incredibly powerful. It can see the subtle curve of the road ahead, detect a small animal near the roadside, or measure the exact gap between two cars. It works perfectly in the dark, as it provides its own light source. However, LiDAR is not perfect. Heavy rain or thick fog can scatter the laser beams, making it less effective. This leads us to the most critical concept in a self-driving car's perception system, sensor fusion. You see, the car does not rely on just one type of sensor. It does not solely trust the cameras, or the radar, or the LiDAR. Instead, it constantly combines, or fuses, the data from all of them. Think of it like a team of experts. The camera says, "I see a red, octagonal sign." The LiDAR says, "I confirm there is a flat, vertical object 50 meters ahead." The radar might add, "I do not detect any moving objects near it." The car's computer takes all this overlapping information, cross-references it, and with overwhelming confidence, concludes, "That is a stop sign, and I must slow down." This process of sensor fusion creates a robust and reliable understanding of the world, ensuring that if one sensor fails or is confused by something, the other sensors can fill in the gaps. But once the car knows what is around it, what happens next? How does it decide what to do? That is the job of the brain, which we will explore in the next part. So, the self-driving car has now created a rich, detailed, and constantly updated map of its world using its fused sensor data. It knows where every car, pedestrian, and curb is. But knowing what is out there is only half the battle. The real challenge is understanding what it all means and deciding what to do next. This is the job of the car's central computer, its digital brain. This brain runs incredibly complex software, and its work can be broken down into two main tasks: prediction and planning. First, let us talk about prediction. The car does not just see other objects as static obstacles. It needs to understand that they are dynamic entities with intentions. For example, when the car's sensors detect a pedestrian standing on the sidewalk near a crosswalk, the brain does not just see a stationary person. It uses machine learning algorithms, a form of artificial intelligence, to predict what that person might do next. Has the person turned their head to look at the road? Are they starting to lean forward? Based on thousands of hours of training data from real-world scenarios, the car's brain might assign a high probability that the pedestrian is about to step into the street. Similarly, it predicts the behavior of other cars. Will that car in the next lane merge? Is the car ahead likely to slow down? Once the brain has a predictive model of how all the objects around it are likely to behave in the next few seconds, it moves to the second task, planning. This is where it decides its own actions. The planning software runs through millions of possible scenarios in a fraction of a second. It calculates trajectories. If I slow down by 5%, I will maintain a safe distance from the car ahead. If I change lanes now, I will avoid that cyclist and not interfere with the car behind me. It is a continuous cost-benefit analysis, weighing the safety, legality, and comfort of every possible move. The final output of this intense computational process is a simple set of commands for the vehicle's controls, a precise amount of pressure for the accelerator, a specific angle for the steering wheel, and a calculated force for the brakes. This is what allows for that smooth, human-like driving behavior. But to execute these commands perfectly, the car needs one more crucial piece of information. It needs to know not just its relative position to other objects, but its absolute position in the world. This requires a map far more detailed than any you have ever used on your phone. Let us look at that next. You are driving and using a navigation app like Google Maps. The blue dot on your screen shows your general location, and the map gives you a rough layout of the roads. This is fine for a human driver, because you use your own eyes to fill in the gaps. You see the lane markings, the exact position of the exit ramp, and the height of the curb. For a self-driving car, good enough is not acceptable. It needs to know its position with centimeter-level accuracy. It needs to know not just which road it is on, but which lane it is in. This is where high-definition maps and a process called localization come in. An HD map is not a normal map. It is a massively detailed, three-dimensional digital replica of the road environment. It contains information that is invisible to a standard GPS. We are talking about the exact curvature of the road, the precise location and height of every curb, the position of every traffic light, the placement of every street sign, and even the texture of the road surface. These maps are created in advance by special mapping vehicles that drive every inch of a road with high-precision LiDAR and GPS systems. Now, how does the self-driving car use this map? As the car is driving, its sensors are constantly scanning the immediate environment. Its LiDAR is creating a live 3D point cloud of the street. The car's brain then takes this live scan and compares it to the preloaded HD map. It is like trying to fit a piece into a jigsaw puzzle. The software looks for fixed landmarks, a specific fire hydrant, a unique crack in the pavement, the exact shape of a building corner, and matches them to the map. By doing this, the car can pinpoint its own location on the map with incredible precision. It is not just a blue dot on a road, it is a vehicle that knows it is 1.2 meters from the left lane marking and 15 centimeters from the center of its lane. This process, known as localization, is what allows the car to plan its maneuvers with extreme confidence. It knows that an exit is coming up in 500 meters, not 450 or 550. It knows the exact geometry of a tricky intersection before it can even see it around a corner. This HD map acts as a form of long-range perception, giving the car a perfect memory of the road. Combined with its real-time sensor data, the car has both a perfect, pre-recorded understanding of the world and a live, moment-to-moment view of it. But with all this incredible technology, why are self-driving cars not already on every street? The final challenge is not just technical, but also about trust and safety, which we will explore in our concluding part. We have journeyed through the incredible technology that powers self-driving cars, from their sophisticated senses of cameras, radar, and LiDAR, to the sensor fusion that creates a unified view of the world, to the artificial intelligence brain that predicts and plans, and finally to the high-definition maps that give them a superhuman sense of location. It is a breathtaking feat of engineering. Yet, the widespread adoption of fully autonomous vehicles still faces significant hurdles. The final frontier is not just about building a car that can drive, but building one that can drive safely in a world designed for, and dominated by, humans. The biggest challenge is dealing with the edge cases. These are the rare, unpredictable, and often strange situations that happen on the road. How does the car handle a ball rolling into the street, knowing a child might run after it? How does it interpret the hand signals of a police officer directing traffic when the traffic lights are broken? How does it navigate a construction zone with confusing, temporary lane markings? Humans use common sense and intuition to handle these scenarios, but coding common sense into a machine is one of the most difficult problems in artificial intelligence. Every possible edge case must be identified, understood, and programmed for, which is an almost infinite task. This leads directly to the critical issue of safety and validation. How do you prove, beyond any doubt, that a self-driving car is safer than a human driver? Human drivers are involved in a large number of accidents, many due to distraction or error. The promise of autonomous vehicles is to drastically reduce this number. But to prove this, they would need to drive billions of miles in real-world conditions to collect enough safety data, a process that could take decades. This is why companies use massive computer simulations, running virtual cars through millions of miles of driving and countless edge cases every day, to accelerate this learning process. Finally, there is the human factor, our trust. Are we, as a society, ready to hand over control? An accident caused by a machine often feels more shocking and unacceptable than one caused by a human, even if the statistics show the machines are safer. There are also complex ethical and legal questions. If a self-driving car is involved in an unavoidable accident, who is responsible? The owner, the manufacturer, or the software developer? These are profound questions that we are only beginning to grapple with. The road to full autonomy is a marathon, not a sprint. But with every technological breakthrough and every mile driven, we are moving closer to a future where our roads are safer, traffic is more efficient, and mobility is accessible to everyone, including those who cannot drive today. It is a future being built, one line of code, one sensor, and one careful decision at a time. Thank you for joining us on this journey into the science behind self-driving cars.